Three, two, one. What's going on, everybody? So I'm actually in a call with people. You're not going to be able to see their Discord icons because I don't know. I just
We
don't.
can't see the stream.
Oh, you can't. Oh shit.
Yeah, we can't see the stream.
Oh, let me fix that real quick. Huh? How does one do this? Go over here, over there. Okay, you guys should be able to see the stream now, right? Testing.
Yeah, we can see it.
Okay, perfect. So I'm going to be talking about geometric inference, statistics, and stochastics, kind of all mumble jumbled together. I think this is a really interesting research direction to like kind of the intersection of these three things: inference, statistics, and stochastics. Because I would say there's a couple of claims that I'm going to be making in this little bit of a lecture, but a statistical model in and of itself is kind of you should think of it from if you're going to get a more geometric account of what statistics is. A statistical model is like a space of laws, not necessarily some like table of numbers, right? As this thing says. And geometry itself allows us to have the language that stays valid under different changes of coordinates. That's what geometry allows for us to do, because we can describe geometric objects by changing between frames, or different things like that. It's also sufficient statistics, which is and also the notion of like when a state lives on some kind of manifold. We're going to be able to use those things and just build these five objects in kind of a strict order. So we'll just kind of do that. Now, convex bodies. I keep talking about this over and over in the Discord. Basically, they're compact, they're convex, and they basically have a non-empty interior. That is what a convex body is. We'll just take that as like whatever that is as axiom. And in order to have convex bodies, they're defined in terms of support functions. And they kind of uniquely determine these the convex sets up to some kind of translation. And there's a special kind of thing called a Minkowski sum, which allows us the operation of adding support functions. And you guys can pause this if you want to, or you can tune me out and read this if you're in the stream. But the Brun-Minkowski Brun-Minkowski, this like theorem, basically allows us to describe the concavity of a polynomial very nicely. And I just want to emphasize that you can there's a particular violet kind of body that I'm showing here, this like convex body, that would be you'd interpret as a O plus TB, and this sand curve here will be designated as H, which is our Minkowski sum. And then the lower panel is basically this kind of square root area law that shows us like, this nice way of the nice property of defining convex bodies themselves. And we can play it kind of how this tends to play out here. And this is like a nice generalization of convexity to defining bodies themselves, and basically size of some addition of Minkowski sets added together, written as a function of the direction itself. Okay, so you can also have like the same morph or read this particular parameterization as a solid itself. So you get like these one parameter families, or one parameter families of convex bodies as three-dimensional objects, and you can rotate basically this camera here as like part of the figure. So we'll see this. It's like rotating it. Oop. So yeah, it's really neat. You kind of have this nice parameterization of your convex body. Now, we can also talk about invariant measures on lines. So once the size of an invariant of a fixed set, basically we're trying to parameterize lines by normal coordinates, essentially. And there's a special kind of measure that we associate with this. It's called a Haar density or Haar measure, which is just dg by dp and d phi, where you have these measures themselves on lines. And there's a very famous formula called Crofton's formula. By the way, I'll have references for the texts at the end of this little talk. But yeah, Crofton's formula allows us to basically say for any closed convex curve, right, the measure of hitting lines itself, or the measure, or if you will, the probability of hitting the lines equals the perimeter itself. So this is a very kind of underrated, profound kind of result, because this we can make like a running estimator of this to converge to this kind of true parameter itself, the perimeter. So you can kind of try to simulate this. And I like this animation. It was pretty fun. Yeah. So I mean, just basically geometry itself is becoming the probability, because this running estimator that we have here for, as we sample it or whatever, it converges to that true perimeter. So yeah, it's quite nice. So for any closed convex curve, the measure of hitting the lines itself equals the perimeter. So it's super, super cool, super useful for probability and stuff. So that's just kind of, this survey, if you will, of trying to entice you to look at geometric probability and geometric formulations of probability. It was very enticing for me. So Crofton's formula. What's next? The manifold of laws. Okay, that's another thing. By the way, are there any questions so far? Any comments? Anything that you guys would think is interesting to point out? If not, it's fine. I can keep going on. Okay, I'll keep moving on. The manifolds of laws. So this is very famous mathematicians, Fisher and Rao. They were interested in describing regular statistical parametric families. So you could have the point itself of the manifold would define some kind of statistic or some kind of regular parametric family that itself is a law. And so you would have a point on this manifold of laws itself, which is pretty interesting. Now you can have the Fisher-Rao metric and define this Fisher-Rao metric that's this statistical kind of metric, and also it's a unique invariant. It is a Riemannian metric, so it's a unique invariant Riemannian metric. And also, I didn't put this as well, but it should be equivalent to, if you were to take this del I L dotted with del JL, it would be equivalent to the negative of the expectation value of with respect to theta of the mixed partials as well acting on L. I don't know why I didn't put that, but I'm sorry. But that's just another property. It's just a Fisher-Rao metric. You can look this up on what it means. But up to scale, you have that it's locally asking how hard it is to tell your theta parameter from some increment theta, plus d theta, right? With one particular observation. So you can look at a univariate kind of Gaussian example of this metric. So this would be a Fisher-Rao metric. And it would be hyperbolic and a Poincare half-plane geometry. And I'll kind of show you guys what this looks like in a second. It's really cool. But you have that, you have these basic unit balls of the metric itself. It's just a diagonal metric. And it shrinks as your variance goes to 0, or as your sigma goes to 0. So it becomes easy to distinguish, and then it swells. The unit balls swell as the variance goes to infinity. And what's also cool are the idea of alpha connections. I didn't give the exact formula for the alpha connections themselves, but it's like a Levi-Civita connection, but you have a special case for the mixture and the exponential things here. So the Levi-Civita connection is when alpha is equal to 0, you get the shortest path for the metric. I'll show you like the sand connection and the oxide connection, oxide colors. But basically, you have the natural parameters that are straight. They're straight, particularly in the natural parameters, and then for alpha negative 1, you have that it's straight in the expectation parameters itself. So this becomes a very interesting geometric kind of metric here. So you have the unit balls themselves of the Fisher metric here, or of the Fisher-Rao metric, and then the Levi-Civita kind of tracing, its alpha equals 0 curve, and then the mixture kind of tracing the expectation parameters curve, and then, but basically, your laws themselves are still the same, like still the same point on the statistical manifold of laws themselves. So you just define different connections, which is very, very interesting and non-trivial, especially as these metrics get kind of more interesting and you start collecting real data and trying to do different things. So yeah, these ellipses here are just slices of a three-dimensional geometry, and you have these conformal factors as well. In the next figure, we'll see here that these same three geodesics are going to ride the surface rather than some flat parameter triangle. That's why they call it a Gaussian family, as being hyperbolic. So you can say these cool kind of connection paths that are more generalized than just the ones that we're used to in physics. Okay, so yeah, a lot of the motivation here is actually for I didn't really mention this, but a lot of the scientific motivation would be for like empirical data, or even like financial markets. I'm not gonna get super into that, but that's pretty much what we're working with. So that's kind of the domain of application, right? So and maybe physics, but I think physics is more concerned with like Arasmanian and Cartan kind of connections as well. That would generalize even further these notions of connections. But yeah, a geodesic as well would be pretty cool to play this one. But these geodesics kind of join the same pair of Gaussians. So you see, like, you have a sample, and then as the time goes on, the geodesic, you have a density evolution that then, is defined by that, connection that's still, a point on that manifold of laws. Now, dual flatness. This is one of the most interesting characteristics, in my opinion, because you have a full exponential family they call it a one flat, right? So you're defining what exactly is flat as your connection. I don't think I wrote that down here, but it's basically like you have the natural coordinates, and then you have the -1 alpha, flat connection that gives you the expectation coordinates for the eta parameter. Okay, and there's something called Legendre duality, where you take psi of theta and psi of eta and define something called the Kullback-Leibler divergence, which is equivalent to the Bregman divergence of alpha, or of psi of alpha is equal to 1 divergence, basically. So we have this equivalence in this duality, or this dual flatness that we can leverage statistically, like with statistical kind of curvature. So you have this maximum likelihood estimation on a curved exponential family that gives you orthogonal projection onto a dual geodesic. And what this can show you, oh my god, it kind of exploded. But what this can kind of show you is the same two laws that look straight on one chart, or on one particular chart, are curved in the other, and that itself is the dual flatness motion, which is pretty interesting, because you're lifting the exponential chart into 3 dimensions by graphing the convex potential itself. And so we can do that and check it out. It's pretty interesting. So this is, on the convex potential itself, we have the exponential path and the mixture path, doing their kind of thing, but we still have the same kind of statistical laws that are being embedded. Okay. So lastly, really, is talking about curved when the statistical model itself is curved. So you have this notion of curved exponential families, right? And we could think about it as what's said to be a smooth manifold, or a submanifold that is not itself a full exponential. So you will have some intrinsic information loss of some efficient estimator in general. So what that kind of looks like is essentially you will have some exponential. Let me see. Yeah. We're still going. You'll basically have like the maximum likelihood estimation that's forcing this kind of ancillary mixture curvature, which is basically when that curvature itself is going to zero. And you can look at basically the height of this ridge here that we're parameterizing for this parabolic model is that this bends, recoverable, where this recoverable information is like the smallest. And as you can see, we really get like that interesting kind of curvature distance here that like maximizes right there, where we can't recover the information anymore. You have like a nice like parabolic bend. Now, obviously, you could do this in like higher dimensions, but it's just nice to see the Efron gamma factor here that's computed for, or the Efron statistical curvature here, the gamma, that's computed for this maximum likelihood estimation, like forcing that mixture curvature, because again they're dually flat. So now what we can do is work with manifolds and diffusions of states on manifolds. So on a manifold, if anybody has ever worked with these types of things, like Ito calculus or Stochastics calculus or Malevin calculus, when you're working with stochastic calculus, you want to ask, is there kind of a geometric curvature that I'm trying to work with? If you are working with some kind of geometry, just automatically assume we're working with the Stratonovich formalism, because it preserves the chain rule and thus is geometric, rather than preserving martingales with the Ito correction. So that's the idea. And on a manifold, if you want to use Stratonovich calculus to obey that ordinary chain rule, you basically have a notion of coordinate invariance as well. That's why it's a geometric. That's why it's a geometric stochastic formalism, and why we use that in statistical geometry. So horizontal Brownian motion on this orthonormal frame bundle can be defined as these little increments. And, like with the Stratonovich kind of, I didn't put everything. I'm giving a qualitative kind of view, so people can listen to it and get an intuition for it. But the generator of this particular, of the horizontal Brownian motion on an orthonormal frame bundle is called the Laplace-Beltrami operator. And we can look at a specific sphere example here, where we have this motion, or the generator that's this half of the Laplace-Beltrami operator. And as you can see, it's pretty cool. It's pretty damn cool. Nice little, it's basically, we're generating the paths on the sphere. And, it's basically, you can think of it as a radial projection of these tangent Gaussian increments that keep the paths on S2. So, your expectation value of your z of t, right, of your your z of t on this projected coordinate for just this nice sphere, you basically see that Brownian motion on this manifold is like rolling without slipping, like if you're going to think about it like as a physical thing. And the projection itself is not itself a random walk in coordinates. You have this frame that kind of makes this horizontal lift uh, over here. So you can see that a point on the sphere itself is not enough. You need a rolling frame, two tangent vectors to be carried without slip, so that we can basically make that visible. Okay, or make the frame itself visible as this orthonormal frame bundle of these Gaussian increments. So I'm just going to close it out here. Basically, what I'm trying to claim is that you're measuring convex bodies and by the Minkowski sum, or sorry, you have convex bodies measured by this h up here, which is the support function. And then with the support functions, we can do Minkowski sums that give us the Brun-Minkowski concavity, so that we have the support functions and ensure that the convexity conditions are met just by definition. And then the Crofton integral allows us to just kind of turn length into these integrals against these invariant measures, which, if everybody knows, that's probability itself, a geometric kind of motivation for probability. That's a lot more fundamental of an interpretation. You have the regular family that carries the Fisher metric and these kind of interesting studying these statistical metrics that give you dual alpha connections. And then you have the exponential family that's dually flat by this Legendre transform of psi itself. And then you embed the curvature into a submodel here, which allows us to have a curved submodel, and then that's the information that the maximum likelihood estimator cannot recover. And then you have Riemannian, this Riemannian motion on this sphere, basically, where you have the projection of this horizontal motion on the frame bundle with the Laplace-Beltrami generator. So just to kind of close everything out, you have these Bonesson, Frenchel. You can check out my website as well. It's on the finance resources, but Bonesson, Frenchel, Santolo, Amari et al., and then Ikeda and Watanabe for their stochastics and differential equations and diffusion processes on manifolds and all of those things. But yeah, that's pretty much everything. Are there any questions or any things that you guys would like to say or?
Yeah, can you go over again on why the horizontal Brownian motion is like the chain rule on the manifold, like the equivalent of the chain rule on the manifold?
Oh yeah, of course. So you basically when you have this is like stochastic calculus. When you have Ito, the Ito formalism of stochastic calculus, that requires that the underlying process is semi-martingale, which basically means it's I think you're familiar with that. But
Yes.
the stochastic or the Stratonovich formalism does not require. It actually violates the martingale condition, but it preserves the chain rule itself. So instead of doing if you do Ito's lemma, you'll have that Taylor expansion with 1/2, times that curvature term. Instead, the Stratonovich kind of relies on a metric for the curvature term, if that makes sense. And that itself, is it's more geometric. The invariants that you want to talk about that aren't martingale with Stratonovich are going to be more geometrical, if that makes sense.
Yeah. So I'm assuming that's the same reason why the generator has the 1/2 term out front. It's because it's that second order.
Yeah, well, the generator itself,
the chain rule.
The generator itself is defined on a manifold, with a metric, right? So yeah, basically it's kind of like an Ito's lemma, but on a manifold instead.
Okay.
Yeah,
that's very interesting. I've never known that it could be applied to this type of field.
It's pretty interesting. I do really enjoy these formulations of statistics with geometry. I think it's kind of underrated. And there's a lot of hedge funds that work. Well, there's a lot of hedge fund managers that have a background in geometry, like one of them being Jim Simons, right? And he worked in differential geometry. He was a geometer, like first and foremost. Integral geometry and like all of these things. Like I think it has something to do with the I don't know, maybe this is kind of conspiratorial, but I think there's definitely some correlation and some secrets in differential geometry that are just waiting to really be played around with in statistics, so and formulated in that way. But that's just my opinion. Yeah, if anyone else has any questions, any comments?
Is that 1/2 number in the generator? Is that wrong to interpret that as being related to like a 1/2 spin, or is that totally different?
I would say that it's different. Think of it more like, I mean, this generator itself is a Laplacian, right? It's a Laplacian defined on the manifold. So it's like, assuming 3 dimensions of space, right? And then we're technically on S2. So, yeah, I should be able to calculate what this actually is, but it's not coming it's not on the top of my head right now. but yeah, I don't think it has anything to do with spin. Spin is more of like a representation of, basically it has to do with the representation of SO3 and yeah, like Casimir operators and the Lie algebra of all that stuff. That's like more of the geometrical understanding of spin versus like, this is just an operator for defining these Brownian increments on a sphere.
I see. I guess the neuron activation I had was that, obviously you have Brownian motion, which is usually often used to describe like fermions, and they have the 1/2, and so I just 1/2 neuron activation. I just had to see if that was had any relation.
Yeah,
to that.
No, it's fine. Sometimes you have to gamble or shoot in the dark on something. I'm totally for it. I think people should be comfortable.
Really cool stuff.
Yeah, I think people should be pretty comfortable shooting in the dark, just asking questions away. That's how you learn. Yeah, if there's nothing else, I hope you guys enjoyed the visuals. These were pretty fun. These were pretty nice. I like these animations. Yeah, if that's everything, then I will.
Were there any Landau volumes that covered this stuff?
Not in particular. Landau's more of
Landau.
Landau is more of like physics type of environment for training.
I was wondering if the statistics volumes covered any of this.
Not implicitly.
I noticed you didn't have it in your.
Yeah, not implicitly. It's more so Landau teaches you how to think about measures, and statistical measures, and like the idea of like measures with statistical ensembles, like a Gibbs grand canonical ensemble, or they call them ensembles in physics. It's kind of it's roughly the same thing. There's kind of a bit of translation that happens between math and physics, but ensembles and constructing ensembles to give you like Gibbs canonical measures and like chemical potentials. These are like more the physical motivations for statistics that actually I would think would be an interesting exercise to see how it relates to these geometrical notions as well. Who knows? Maybe there's a connection there that I haven't really connected yet. So yeah.
I thought the dual flatness stuff was interesting. I was gonna try to read more about that.
Yeah, for sure. If you remembered anything from that, just maximum likelihood estimation.
Interesting.
Yeah, maximum likelihood estimation with like, recovering or stuff that can't be recovered from that, like being dual to the exponential family. Yeah, it's pretty interesting stuff. And a lot of this is old. and it doesn't really get talked much about, like much. So I want to revise it or revive it for my audience. I think they'll find this interesting.
Were you gonna post this today?
Yeah, I'll probably post it in the morning or sometime in the morning. But
Okay.
yeah, okay. Well, if that's everything, anything else? You guys have any questions? Any more questions? All right. Well, it was a pleasure. Thank you guys for joining, and I will see you guys next time.